So, here's something you may have never given much thought. What does Venus look like? If you look at pictures of it, you'll see either depictions of it as this scarred rocky planet with a bright orange surface or as a ball completely obscured by swirling yellow clouds. Particularly, if you look for a clip art of it, it feels like there's nothing these drawings all agree on other than that Venus is somewhere in the range of yellow to red. But is it? No, really, think about that for a second. Have you ever seen Venus? It's the evening star at the time of recording, visible just after sunset, and, as it's been for millennia, it's a small off-white dot in the sky. Obviously, Venus can't look like this, and this, and this, but even through a good telescope it's hard to make out enough detail to tell which of these images is the most accurate, so what's going on with these images, and what does Venus actually look like? There's about a dozen different images I've seen of Venus floating around in the media. Each of them is made with data from one of the 35 probes that have visited the planet since the 1960s. I'd like to take a look at the specific technology and history behind some of the more questionable ones here, before trying to piece together what an accurate Venus should look like. I want to start with this image, composed with data collected by the Magellan probe in the early 90s. Magellan's mission was to map the surface of Venus in detail for the first time, except Venus's atmosphere is far too thick to photograph the surface, so how was this photo taken? Well, it's not a photograph. This is a synthetic aperture radar map. Synthetic aperture radar, or SAR for short, is a bit like flash photography, except instead of sending out visible light to capture, it uses radio waves. This would allow you to pierce through the atmosphere, as clouds and gases are effectively transparent to radio, and by measuring the timing of the signals to return, you can also calculate the distance to each point, allowing the creation of an accurate topographic map. However, because the wavelengths used are in the centimeters, and the sensor to detect them isn't that much bigger than that, there's a physical limit to the angular resolution of the image you get. This is where the synthetic aperture part comes in. By taking a series of measurements as the satellite orbits the planet, we can see what we would have gotten if the satellite's sensor were as long as its orbit, effectively simulating a camera with an aperture miles wide. The actual math and algorithms needed to do this are far more involved than I'm letting on, but by orbiting Venus nearly 1,800 times and synthesizing the data on a computer, the team at NASA was able to create a map of the entire surface of Venus, minus a few spots, with enough detail to see volcanoes, craters, and other geologic features, alongside a topographic map of the solid surface of the planet. However, the images we get from SAR need to be interpreted a bit differently from a conventional photograph. For example, when SAR is used on Earth, flat surfaces like bodies of water that reflect but don't diffuse light appear black on the resulting map, as the beams sent toward them got reflected back into space rather than back at the satellite. That's also how the SAR maps of Titan show the moon's hydrocarbon lakes. The lakes aren't actually blue, but because they diffuse light at a level below the land surface, these false color images were created with dark regions tinted blue and bright regions tinted gold as an artistic choice. Likewise, the Magellan map of Venus was colored with a burnt orange, which paints a picture of Venus as the fiery hell world we know and love. As for how Venus would actually look without its atmosphere, no one really knows. There are a handful of color photos for the Venera 13 and 14 landers, and they are, in fact, very yellow. But this yellow isn't the color of the rocks. The cameras on both probes had red, green, and blue channels, and in the blue channels the probes returned pretty much nothing, which indicates that these aren't the sort of lighting conditions we're used to on Earth. The yellow color here is actually a result of the diffuse incident radiation that's able to seep through Venus's thick atmosphere. Measurements taken by Venera 11 show a sharp fall-off in the intensity of blue light as you descend into the atmosphere. What exactly is absorbing these blue wavelengths is, at the time of writing, unknown. You might assume it's all the sulfur, since elemental sulfur is yellow and Venus's clouds is sulfuric acid, but optics aren't really that simple. Eggs contain sulfur, but that's not why yolks are yellow. The sulfuric acid clouds, which make up the upper layer of Venus's atmosphere, are actually pretty reflective in all wavelengths, giving them a white appearance. But because those clouds are occasionally broken up, it's known that there's something in the air below that's absorbing more blue than we'd expect. Knowledge of this layering actually goes all the way back to 1927, when astronomer Frank Ross captured images of the planet with an ultraviolet filter. Through this, dark markings were clearly visible at all times. When he tried a blue filter, the markings could be faintly seen only on nights when the ultraviolet images showed strong contrast. But with a red filter, the markings could never be seen. This led him to conclude that, quote, "The apparent white surface which we see is imagined to be a uniform shell of light cirrus clouds overlying a dense yellow atmosphere. On occasions of violent atmospheric disturbance, the uniform cloud covering is broken up and we see the underlying yellow atmosphere, to which are due the dark markings seen visually and photographically." So maybe, instead of understanding Venus as a yellow planet or a white planet and leaving it at that, we should imagine it as white from the outside, but with a yellow glow on its inside. You know, like an egg. That's stupid, cut that part. Getting back to the space race, the first probe to send back images of Venus was Mariner 10, equipped with a television photography system that delivered digital images in a 700 by 832 pixel format, captured by two Vidicon cameras placed behind an 8-position filter wheel, which contained clear, blue, orange, ultraviolet, minus ultraviolet, and ultraviolet polarizing filters, along with a defocusing lens for calibration and a mirror that gave access to a wide-angle optical system. Mariner 10 spent most of its mission imaging Mercury, but before it did so it flew by Venus, imaging it mostly in the ultraviolet. At the time, this ultraviolet image, given a false blue color, was the most influential one to come out of the mission. In 2020, though, NASA engineer Kevin Gill used data from the orange and ultraviolet filters to construct these images, which is why the one on the right was so ubiquitous during the Phosphine on Venus news cycle. Later missions that studied the atmosphere of Venus, such as Pioneer 12, Messenger, and Akatsuki, also primarily sent back images in the ultraviolet. And why wouldn't they? You can learn far more about the structure and rotation of Venus's atmosphere when you can see detail beyond just a plain white orb, so imaging in visible light is a bit of a waste. It's understandable that space agencies would be most proud of the images that show the most engaging scientific discoveries, and these are the same ones that the press uses to remind the reader of why these celestial objects are so intriguing. But what does that leave us with? There are two images I've seen bandied about as depicting Venus in true color. First, the less common, this one, which has been listed on the Wikipedia article from the Mariner 10 probe as Venus in real colors since 2006, which is not entirely accurate. This image was compiled by Ricardo Nunez in 2005, who states that the image was processed from Mariner 10's clear and blue filters. Except the Mariner 10's clear filter still let through a considerable amount of ultraviolet light, so the cloud structure visible in this image is likely more pronounced than it should be. He also stated that, to get the colors right, a yellowish global hue was assumed, so it's not certain from that this is a true color image. This leaves us with one image. This is the image that has been bothering me for the past 6 months. It was created by Gordon Ugarkovich in 2009 using data from the Messenger probe's red, green, and blue channels. It was soon posted on planetary.org in an article titled "Venus Looks More Boring Than You Think It Does," which noted how in most depictions of Venus, the cloud structure is shown through a UV filter, but in true color it's nearly as featureless as a cue ball. The image began to pop up again throughout 2021 and 2022 on Reddit, Twitter, and an article in The Atlantic, all noting how strange it seems that Venus is this white when until now they believed it's quite yellow. However, I think it's worth asking, how can we be sure that this image is correct if all the others are wrong? To find out, let's take a closer look at how this image was produced. The Messenger probe, much like the humble mantis shrimp, can see in 12 colors using its filters. These filters range from ultraviolet to infrared, but the ones we want to focus on are these three, the 630, 560, and 480 nanometer filters. These correspond about with the wavelengths of red, green, and blue light, so we can just throw images from these together in the RGB channels of an image and that should be what Venus looks like, right? Well, there's a bit more to it than that. If you look at the probe's CCD data directly, there's a significant amount of noise that results from factors like manufacturing defects and the extreme temperatures experienced by the probe in space. To account for this, we need to perform flat field correction, essentially subtracting from the raw image what you would get if you had the sensor running with no incoming light, and then dividing that by what the sensor returns with a constant known light source. Additionally, the stored value for each pixel, referred to as a digital number or DN, doesn't necessarily have a perfectly linear relationship with the actual number of photons hitting the sensor, so experiments of the responsiveness at different exposure levels had to be performed in order to model the radiance of the light entering the camera. Because the Messenger probe took all these measurements at various stages, in 2016, the USGS uploaded an archive of calibrated data from the Mercury Dual Imaging System stored in a 16-bit format measured in watts per square meter per micrometer per steradian, units of spectral radiance. That per micrometer there indicates that these values represent the intensity of light at a particular wavelength, as part of a complete spectrum. And because these are narrowband filters we're working with, you can think of these values as just a few points of data hinting at the shape of the full spectrum of color. What does that spectrum look like? Well, using a model of the disk average spectrum of Venus from the Virtual Planet Laboratory, we can see that the radiance measured in the red, green, and blue filters, along with measurements captured in ultraviolet and into the infrared, fit fairly well on a curve just under the spectrum of sunlight itself, with a noticeable drop in the blues and ultraviolets. Interpolating between these points to model a complete spectrum, we can use the CIE XYZ standard observer color matching functions to integrate over the visible wavelengths. Then, these XYZ chromaticity coordinates can be converted to sRGB, the standard color space for modern displays. This should give us, at least in terms of what can be displayed on a screen, as close of an approximation to the true color as we can get. So I did this myself, using data from these 7 filters captured around the same time, to construct an approximation of the true colors across the whole image, and this is the result. Not too different from the image posted by Ugarkovich. There's some variation in the colors you can get depending on how you interpolate between these points, but every way I tried still gives a result firmly within the range I'd call white. I reached out to Ugarkovich to check if he'd done anything differently, and from what he told me, he used data measured on the ground for calibration rather than in-flight measurements, which gives a slightly wider result than what I got using the data calibrated by USGS. Either way though, it seems safe to say that, to the human eye, Venus would appear a lot more white than we might believe. And this shouldn't be too surprising. There are plenty of images of Venus taken with decent detail through a telescope, and though these vary a lot, many show the planet as white, though, like the sun, it can appear more yellow as it gets down to the horizon. This still leaves me wanting more though. Regardless of the color, isn't it obnoxious that the only visible light image we have of Venus is cut off from the sides like this? Looking at other images taken by Messenger, all the rest taken on this approach were done much closer, and there's not even enough here that I could piece together a full hemisphere. So I went back to the Mariner 10 data. That didn't have proper red, green, and blue filters, but using the interpolation trick I described, I can use some of the orange, blue, and ultraviolet images to reconstruct what it would have looked like in visible light. The data has gone through decades of processing and conversion, and a lot of the images look like this, so I did a lot of manual tweaking to get it to look clean. The data also wasn't stored in any particular units of radiance, and it was clear that the brightness of each frame was impacted by the darkness of the lens as well as variations of exposure, so I adjusted it specifically to match the colors of the messenger image I got. That means if you don't trust what I did with the first one, you shouldn't trust the other one either, but I'm happy with how they turned out. Now, with Venus out of the way, would it surprise you to learn that, to the human eye, Mars is white? No, I'm just kidding. All the other planets look pretty much how you'd expect them to in real color, though perhaps with a bit less saturation. The one exception is Mercury, which most clip art seems to show as brownish, though there's a lot more variation here than with Venus. I imagine there's less of a cultural consensus on what Mercury looks like just because people don't really think about it as much. In a small survey I conducted, nearly half of the respondents ranked Mercury as the least interesting planet, so Mercury being gray feels appropriate. I went through a lot of those tacky children's wall decorations of the planets, as that seems pretty indicative of what people might grow up thinking the planets look like, and god are some of these terrible. A fun game is to go through these and try to guess which planet each of them is actually supposed to be. Like in this one listed on AliExpress. What is this rocky blue planet? The label says it's Uranus, but no it isn't. As far as I can tell, this is a piece of art composed from various pieces of the Martian surface, flipped, rescaled, blended together, and recolored, created to be sold as a generic 3D planet fluorescent wall sticker removable glow-in-the-dark sticker, and then passed on to a new design team for an all-planet sticker pack, who then just had to make a rash guess as to which planet exactly this one was supposed to be anyway, and just went with Uranus. Or, in my absolute favorite collection, apparently sold at some point from GP Digital, a casting of the Sun in fluorescent red, Mars as the Magellan probe's rendition of Venus, and Venus as, get this, Mars, Uranus as its moon Miranda, Saturn as, well, this rocky planet, which I believe originates from an Adobe stock image of a 3D model, and finally, Earth, with the Blue Marble 2012, a composite image that I honestly think betrays the spirit of the original Blue Marble photo as it uses a really awkward fisheye-like projection that makes Mexico look like it's the size of Asia, except it's been passed around as if it's an honest depiction of the Earth enough that I already have an entire extra rant to go on about how much I hate this specific photo of the Earth, not to mention that this one has a saturation dialed up for God knows what reason. Look, I don't want to act as if poorly designed glow-in-the-dark sticker packs for children are the source of all society's problems, but I do distinctly remember growing up under the impression that Pluto was purple because of one of these, and being deeply confused when I saw images from the Hubble Space Telescope showing Pluto as orange and black. Actually, fun fact, did you know that we've never seen what the south pole of Pluto looks like? Pluto's orbit is extremely slow, so which side is facing the inner solar system only changes over the course of centuries. By the time telescopes were good enough to see its surface, by which I really just mean Hubble, Pluto had just passed its equinox, so when this map was created in the summer of 1994, only down to around 77 degrees south latitude could be seen. When these more famous scans were imaged throughout 2002 and 2003, it could be seen down to around 60 degrees south. Pluto's south pole could have been visible as recently as 1988, so Hubble was just barely too late to image it. By my calculations, our next chance won't be until July of 2107, so until then, really anything could be there. Probably just aliens, though. The color of Pluto is itself an interesting story, though. Like, this image here is described on Wikipedia as Pluto in true color, taken in 2015, but the camera on New Horizons didn't have a green channel. When New Horizons made a closest pass in 2015, this is the high-resolution photo everyone saw, which used the camera's infrared, red, and blue channels, though a few months earlier, NASA had released this image as a, quote, global mosaic of Pluto in true color, though it's not entirely clear how the colors here were determined. The one now on Wikipedia was created in 2018 using processing to approximate the colors that the human eye would perceive, though again, I'm not entirely sure what the process is. With more time, I might try learning how to compile these images myself from the raw data, but it seems quite a bit more involved in the messenger probe data, so for now I'd just like to reflect on how claims about the true nature of something tend to spread online. Common misconceptions are a funny thing, in that any attempt to correct the general understanding of a topic can get swept up in the same patterns of relying on the few sources and clarifications that make themselves available to the most people. This one off-center messenger image, though more accurate than other depictions, is just one way for us to visualize a body that none of us will ever really see up close. So even though I believe it's right about the color, I don't think it's great to rely on a single source when most people don't even know how it was assembled. I think the solution is for science communicators to be more detailed in general about how the images and information they're presenting to the public have been put together. That's why I wanted to make this video, not just to answer the question of what Venus looks like, but to answer how we know what Venus looks like, so we can be better equipped to understand scientific data in all forms. As for Venus in particular, I think the tide has already begun to shift towards white Venus being accepted as the norm. If that comes to pass, this whole video may seem somewhat dated, but I suppose I must always resign myself to be a product of the times. Whereas I grew up with fanciful depictions of a cloudy and mysterious yellow planet, and the engineers who built the probes of the space race grew up hearing of Venus as a world that could have anything from oceans to jungles to sprawling cities, kids today who look up what Venus looks like will be faced with this white orb, passed on as the true look of the planet. Perhaps a bit enlightened, perhaps a bit disillusioned. I still believe that the only true way to understand the look of Venus, at least to human eyes, is to just look at it yourself, as people have done since before there were people, and there's no harm in mythologizing it, whether as the morning star or the ashen light or that trace of phosphine that everyone hoped meant aliens. Either way, Venus is Venus. That point in the sky will always be somewhat detached from what people actually picture when they think of Venus, so who cares if you saturate it a bit? So yeah, this has been a new style I'm trying out, as usually I just post this on my blog and leave it at that, but I might try to make more videos like this in the future, depending on if other people like this one. If I do, then the next one will be about calendars.